So thank you very much for being here. We're very happy that Sigurd Angenent is our speaker today, and he'll give a talk on non-uniqueness in mean curvature flow and Ricci flow. Thank you very much, and please go ahead, Sigurd.
Okay, well, thank you very much for the introduction, for the invitation and for the introduction. I really like these online seminars. It's a really great opportunity for people from all over the world to go to talks that they normally wouldn't see. Okay, so what I want to talk about today is so non-uniqueness in mean curvature flow and Ricci flow. So first of all, it is joint work with Knopf, Velazquez and Tom Ilmanen in the audience. Hi, Tom. And also with Dan Knopf in Austin. So the motivation is finding examples of solutions to mean curvature flow that form a singularity, and then after that have more than one continuation, and also to get an idea of how many continuations there are, how strong the non-uniqueness is. And so I said for mean curvature flow, it turns out that we can do something similar for Ricci flow as well. So we begin by mean curvature flow. Mean curvature flow, as a summary, I'm thinking of mean curvature flow of, well, in this talk, all the hypersurfaces will be embedded. So it's codimension 1 hypersurfaces in our, and it will always be in Rn, not in Rn plus 1 like I wrote here, but so that doesn't matter that much. So the equation for mean curvature flow is velocity equals mean curvature, where the normal velocity is the normal component of the time derivative of the parameterization, and the mean curvature is the normal component of the mean curvature vector, which is the Laplacian of the parameterization with respect to the metric, the induced metric. Okay, and then there's, if you have a compact, smooth, initial immersed hypersurface, there always exists a solution for at least for a short time. The equation, if you switch the normal to minus the normal, both v and h change their sign. So this equation, mean curvature flow, is does not depend on the choice of the normal, and the immersed hypersurface does not have to be oriented. So you could, if you wanted to, try to evolve a Klein bottle and see what happens. Okay, so here's a picture of a hypersurface with the outward normal. At this particular point, the mean curvature is pointing inward. So in my convention, h here would be negative because the mean curvature is in the opposite direction of the normal. In particular, for me, spheres with a sphere, if the unit normal is outward, the mean curvature will be negative because the curvature vector is pointing inwards. Okay, so there are variations on this theorem if your initial surface is not compact, but is the embedding is proper, so the manifold is not compact. So think of an unbounded embedded surface. If the initial surface has bounded second fundamental form, then there still is a solution. The short time existence result still holds, and you could also try to prescribe boundary conditions. So there are many other variations on this flow. In fact, all these solutions that I'm going to talk about are of this type. They will not be compact. Okay, so there are special solutions. So here's a list of kinds of special solutions that we're going to consider. There are stationary solutions where the solution does not depend on time. In this case, the mean curvature flow equation reduces to mean curvature 0. So these are minimal surfaces. Then there are translators, which are being studied a lot these days. So these are solutions where the surface at time t is the initial surface plus t times a fixed velocity vector. So these are solutions that translate in time with constant velocity. They satisfy this equation. Note that these equations on the right are all h plus some lower order, something that does not involve that does not involve second derivatives of the surface. Okay, and then you have shrinking solutions that exist for all negative time, where the solution at time t is given by is a dilate of a fixed surface n. That surface n has to satisfy the so-called shrinker equation, which is this. And then and I'll show you examples of these. Then there's, for positive time, you can look at solutions that expand. So these would have to be surfaces that satisfy this equation. So the shrinker and expander equation are almost the same, except for that sign, plus or minus. Okay, so here are some pictures of solutions. So this is a minimal surface. There are many of these. These are shrinkers. Shrinkers in general are of the form Sk cross Rn minus k, or the convex shrinkers. So they're generalized cylinders. This thing is not convex. It's a shrinking donut, so it has the topology of a torus, and it shrinks to the origin, which is right here at the center of mass of the surface. So these are all shrinkers. So these all satisfy H plus 1/2 x dot n is 0. Here you have the simplest example of an expander, which is the bracket wedge. Now, the initial condition is 2 lines. So I drew line segments, but I mean the whole infinite line. Of course, one can never draw an infinite line, but there's a bit more of the line. So if you take that line, those 2 line segments as initial curve, then there exists a smooth solution. It has to be self-similar, and so it is of the form, it's a curve, so curve at time t is square root t times the curve at time 1. And that curve at time 1 is this particular red curve. It's asymptotic to the 2 lines. So this example is it's a template for many other examples to come. This picture is from Tom's website. This is an example of a self-shrinking, self-similar shrinking solution that is computed. So I included here to just to emphasize that there are many shrinking solitons that are have great topological complexity. Like this thing has high genus. The number of holes here is I should have counted them. I think it's 8. Looks like 7, 9. Probably 9. So that can be chosen to be arbitrarily large, and then there's an existence theorem for this thing. So again, this is a shrinker. Right, this one satisfies H minus 1/2 x dot n is 0. And this is a translator. This is called the bowl soliton. So this is the simplest translator is a curve in the plane called the Grim Reaper. That translates in that direction with constant velocity. And there's an explicit formula for it. The higher dimensional analog of that thing is something that has the shape of a paraboloid, but it's not exactly a paraboloid. But this thing satisfies H plus 1/2 x dot. And now the velocity vector is this. So it satisfies that equation. So this is a translating soliton. So in this talk, we're going to be, I'm going to be talking mostly about expanders and shrinkers. And these translating solitons will not show up. Minimal surfaces are sort of in between translators and shrinkers. They will play some role. Okay, so go back very far in history. There's with Tom Ilmanen and David Chop, we studied expanders from cones in 3 dimensions. And I should take a step back. There is, so what is a cone? A cone consists of 2 parts. So if you take 1/2 of the cone, you get You get something that looks like this. It's like a Melita filter. So this is a graph. So this is half a cone. And this is a Lipschitz graph. There's a theorem by Ecker and Husken that says that if you take any Lipschitz graph, then there is a unique mean curvature flow forward in time. And then from the fact that the initial condition is self-similar, if you dilate this cone around the origin being at the vertex of the cone, right, so it's the graph of z equals square root x squared plus y squared. If you that surface is invariant under dilations, so the solution should inherit the same symmetries, and that tells you that it's a self-similar solution. It's an expander. So there is a solution that expands from this cone, and it's the three-dimensional analog of the Brachet wedge that I had over here. Okay, so if you have half a cone, there is a unique forward evolution of that thing. So if you take a full cone, then there is at least one way to evolve this thing forward in time, namely the cone could break into two parts that expand, and that just one half moves to the right and the other to the left. Okay, and they will both be self-similar solutions. So if you have a cone and this opening alpha is an arbitrary number between 0 and 90 degrees, there will be at least one self-similar solution, and that's the one that is drawn here in this picture. Now, it turns out that if the angle alpha is large enough, bigger than roughly 58 degrees, and that number comes from numerical computations of these solutions, then there turn out to be two self-similar expanding solutions that are the topology of that are connected. So in this case, the forward evolution of the cone is like this. If you start with the cone thus, then in forward time, it expands like this. Okay, so this is an example. So if these cones where the opening angle is large enough, bigger than 58 degrees, are examples of initial surfaces that have one singular point, and where you have at least two, and in fact here, three forward evolutions in time. So this is an example of non-uniqueness for the initial value problem. Now the question is, could there be a smooth? Is there a smooth solution that forms a singularity for negative that exists for negative time, forms a singularity, and at time t is 0 gives us this cone with an opening angle bigger than 58 degrees, and that so it can't be a rotationally symmetric solution because let's see, it would have, if it's asymptotic, so there are no rotationally symmetric shrinkers that do that. There can not be an arbitrary shrinker because using the result of Lu Wang, you have to prove that the solution has to be rotationally symmetric. So this is this example gives us half the example, satisfies half the motivation. We have non-uniqueness of the forward evolution, but we don't have a smooth solution that forms this singular initial condition. Okay, so and in the paper with Tom and David Chop, we argued that there's computational evidence that there exist solutions of with more complicated topology that have shrinkers that look like two cones that are not exactly, that are topologic, they're asymptotic to cones, and they are connected by tubes, and they're very difficult to draw by hand. So you have two things that are cones, but they don't have exact circular symmetry. You could arrange for them to have reflection symmetry about these two lines that I drew, or planes. And so there's a self-similar shrinker. There's computational evidence for a self-similar shrinker of this type that forms a conical singularity. And you can measure this thing, and you can show that the opening angle here, the minimal opening angle, is bigger than that 58 degrees. So this would be a solution that has more than one forward evolution, self-similar forward evolution. The existence of this thing, as far as I know right now, is the evidence we have is this numerical computation done by David Chop. But there is a lot of work on minimax arguments constructing shrinking solutions, and I would assume that in the near future, someone will prove the existence of something like this. Okay, so let's leave 3 dimensions behind. So then we look at higher dimensions, and to make life easier, we'll look at things that have not rotational symmetry, but symmetry under a different group. So you can think of the symmetry is that the solution hypersurface should be invariant under the action of OP and cross OQ, where OP acts on RP and OQ acts on RQ. P equals Q is M. And our hypersurface is n minus 1 dimensional, sitting in Rn. Okay, and so these hypersurfaces are all of the form of points xy in Rp cross Rq, where the length of y is equal to some function of the length of x. At least surfaces of this type have that kind of symmetry. So, and you can think of this as taking a graph in the first quadrant, y is u of x and t, and swinging it around the x-axis in a certain number of dimensions, and q minus 1 in q dimensions, and swinging it around the y-axis in p dimensions. And this gives you then a hypersurface. That hypersurface MP evolves by mean curvature flow if and only if the function u satisfies this partial differential equation, which is considerably simpler than mean curvature flow because it's a parabolic PDE in one space dimension. The function is it's a scalar. It's PDE for a scalar. It's a quasi-linear PDE. So there's lots of standard theory that you can use, regularity theory that you can use to deal with this. It has 2 places where there are problems. One is here at x is 0. So at x is 0, namely here at this axis, we have a 1 over x du dx term, which is analogous to the Laplacian and polar coordinates. So the Laplacian and polar coordinates looks like this. So this middle term is of this type, and you can deal with it in the same way that you can deal with the n minus 1 over r du dr term in rotation symmetric PDE. The other term that is problematic is this one. When u gets close to 0, this term blows up. So your solution has to be positive. If the surface ever does this, what you would get is a neck pinch. And the type of neck pinch that would happen here is a q minus 1 dimensional neck would pinch off. So we'll be looking at self-similar solutions to this equation. The simplest solution is are the stationary solutions. So they are given by the following. So stationary solutions are solutions to this equation. So you just set the time derivative equal to 0. So this, and again, this equation is equivalent with h is 0. And in this setting, for this ODE, they were studied by Alan Carr in the 1980s. So there's a very special solution of this. So it's a second order ordinary differential equation. so it shouldn't be too hard to analyze. Right? There's a very special solution that you get if you look for cones. It turns out that the cone y is equal to ax is a solution if and only if this slope is given by square q minus 1 over p minus 1. For most of the talk, you can assume that q and p are equal to each other, and then that number a is just 1. In fact, for most of the talk, you can ignore many of the equations that I'm writing. I just want here. I'm putting them here so you can see what they would look like if you had to do it. Okay, so Alain Kars analyzed this equation by reducing it to a phase plane. So one way of doing that is to look for two scale invariant quantities. So if you x divided by u, x and u are both lengths, so this ratio has no dimensions or has no units, and the u dx also has no dimensions, or they're scale and dilation invariant quantities. So these quantities satisfy an autonomous system of first order equations, which looks something like this. And the only thing that's important for this system of equations is the following. There's a fixed point, x and y both equal to 1. That fixed point corresponds to, so if x and y are both equal to 1, then that tells you that u is a times x, right? And the u dx is a. So I want to draw the phase planes that go with this. And the phase planes that you get depend a little bit on they depend on the dimension, the dimensions p and q. So p and q together are greater than or equal to 8, and p and q both are not equal to 2. There's one exceptional case. Then you find that there are two fixed points, one at the origin, one at the point 1, 1, and there exists a solution connecting them, and that solution corresponds to a minimal surface. So 0, 0, that fixed point corresponds to starting on the x-axis somewhere. So this is the phase plane. This is x, u of x. So this is so this gives you a solution. So the cone is this. This is the curve. If you rotate it around this axis and around that axis, then it will give you a minimal surface. It will give you a hypersurface of Rn, n being greater than or equal to 8. That is has 0 mean curvature. This surface is star-shaped. If you take dilates of it, then if you rescale it, it does not intersect itself, and in fact, it foliates the whole complement of the region above the cone. So this is the minimal cone. And one of these is Alain-Kars surface. And so Alain-Kars surface is asymptotic to the cone. And so these fixed points exist for when p and q together are less than or equal to 7. P and q must both be greater than or equal to 1. Greater than 1, so greater than or equal to 2. So in this case, that same orbit exists, except if you linearize around the cone, you find that the eigenvalues are complex, and the solution does this. So it spirals in. It's a from your ODE textbook. It's a logarithmic spiral that spirals in towards the point 1, 1. So that means that the hypersurfaces that you get there look like this. So the minimal cone is still this. And the hypersurface approaches it by spiraling, by zigzagging around it like this. So it intersects the cone infinitely often. And if you, the existence of this surface, in particular of this little bit here, shows you that that the cone is not area minimizing, because you could take, so here's the cone, and the little bit that of Alencar surface that I drew is this. And now you can take any dilate of this, and it's still a minimal surface. And so there's a little calculation that you can do, which says that if you say, if you fix this endpoint and you look at the surface, so let me look at this surface, and then you let this point move towards the origin, right? So that the next one you get is this, the next one that you get is this. If you do that, the area of the surface that you get is increasing, and in the limit what you get is the cone. So that means that all these things have areas smaller than that of the cone. So the cone is not area minimized. That same thing does not work in this situation. That same argument does not work there. So for in dimensions less than 8, the cone is not area minimizing. For dimensions 8 or higher, the cone is minimizing, with the weird exceptions where P and Q, P or Q is equal to 2, and the other one is 6. So, and I don't want to talk about that one today. Okay, so we have minimizer. I summarize again. We have the cone is stationary for P. For P and Q equal to 4. Simon's cone, you get the cone that is called Simon's cone, which is famously minimizing. For P equals Q less than 7, they are not minimizing. For P is 2, Q is 6, you get Simone's cone, which is a different thing. To look for expanders or shrinkers, we don't look for stationary solutions. We look for self-similar solutions, and so the calculation that you have to do is to look for solutions of this type. We look for solutions where U, capital U, is a fixed function, and if you put a plus, you get expanding solutions. If you put a minus, you get shrinking solutions, right? So, and they are defined when plus or minus t, the thing under the square root is positive. So shrinking solutions are defined for negative t, expanding solutions for positive t. If you substitute this in the PDE that we had before, you get almost the same differential equation. You just get 2 extra terms, namely this term and this term, each of which has a plus or a minus, depending on whether you're talking about shrinking or expanding solutions. There are boundary conditions at C is 0, where so at C is 0, we want the solution to hit the axis perpendicularly. So its value has to be positive, and its derivative must be 0, and then you get something like this. Right, so this, if you take this graph and rotate it around the 2 axes in the appropriate dimensions, you will get a hypersurface that is either an expander or a shrinker. This differential equation is sort of a random-looking differential equation. It describes the geodesics in the positive CU quadrant for a metric that is conformally equivalent to the metric of the Euclidean metric, and has this factor multiplying it. And this makes more sense once you've heard of Huskins, once you think of Huskins monotonicity formula. So I just don't want to go on that here right now. Okay, so we're going to study, so I do want to expand, say that these are the equations for geodesics, because if you have geodesics, geodesics don't have to be graphs. So solutions could well do something like this, right? They could self-intersect, they can have vertical tangents, horizontal tangents, it doesn't matter. So obviously only a graph-like section of this curve will be the solution to that ordinary differential equation. Okay, so here's a theorem. So we have separate theorems for expanding expanders and for shrinkers. The statements are sort of similar, and particularly the drawing is identical. So let me state this carefully so that you see the difference. So what is this? For expanders, we have the following. First of all, so here's our C and U axes. If you pick an arbitrary value A here, then there is a solution to the ordinary differential equation with the right boundary conditions that starts here for that exists on a short C interval. For expanders, we can show that this solution exists for all positive C, that it is increasing. So UC is positive. It is increasing, and U over C and UC both converge to limits as C goes to infinity, and this limit is a function of this height A, and it's a continuous function of A. Okay, so the expanders that we get all are asymptotic to cones. So this one, say, could be asymptotic to, a better drawing, this one could be asymptotic to this cone. What's more, what we can show is that how shall I say this? If you start with a large value, so the stationary cone would be this. If you start with a large value of the initial height here, you get something that just goes off to infinity like that. If you start with a small value of A, you get a solution that, and now I have to zoom in. And here, what this thing does is it behaves like Alencar's minimal surface. So for a short bit, it behaves like Alencar's minimal surface, and then after that, it just becomes asymptotic to a cone, right? And so the slope of, so this would be U of A, C, and this height is A. Okay, if you make that A even smaller, what happens is that this asymptotic slope changes, may go down again, and your next solution could be, sorry. Right, your next solution could be this. It's also asymptotic to a cone, has more intersections with a stationary cone. So other facts that we can, prove is that sorry. This converges to a special function, let's say called U0 of C, and the graph of this thing is the Alencar solution. So this is as A goes to 0. Okay, so that's in an equation what I was describing here. If you choose this initial shooting height smaller and smaller, then the initial segment of your solution looks more and more like the Alencar solution and has more and more intersections with the stationary cone. So in particular, the number of intersections of u a c with y is a c. This is always finite, but it goes to infinity as a goes to 0. Okay, and in particular, if you do an analysis of the asymptotic slope, you find that you find this graph. So the pertinent statement is so I'm really sorry. This statement doesn't make sense. So I will formulate this correctly. Okay, so here on the right, I have the graph of the asymptotic slope. So for given starting height A, there exists an expanding solution. It is asymptotic to a cone with slope A plus A, little a. As A goes to 0, that slope converges to the slope of the stationary cone. And for all, so for any n, there is an epsilon n such that for all a, I'm sorry, I understand what I wrote. This dot doesn't belong here. So this is one sentence. Okay. So for any n, there is an epsilon n such that for any a closer to a less than this epsilon n, there exist at least n different shooting heights where the asymptotic slope is equal to a. So in this picture, on the vertical axis, we have the asymptotic the asymptotic slope as a function of little a on the horizontal axis. Little a ranges between 0 and infinity. The slope ranges between 0 and infinity. As you let a decrease, the asymptotic slope converges to this value, but it does so in an oscillatory way. And so if you choose your height a here close enough to, if this is a given value of a, then how many expanders are there that are asymptotic to the cone with aperture a? They are all these. Right, so in this picture, there are at least 6 of these. There are 6 values. So if I look at a cone that is sufficiently close to the stationary cone, then there are at least 6 expanders that are asymptotic to that stationary cone. Okay, so what does this mean? This means that if this is the stationary cone, and if I want to have a cone that has, for which I have at least 6 different solutions starting from that same cone, then I should take the aperture of that cone sufficiently close. So this is this is the stationary cone. Now this one has a plus minus a dq less than epsilon. Now there are at least 6 solutions that start from this cone, right? So that is the same statement that I had all the way in the beginning. Right here in the 3-dimensional case, here we had 3 solutions starting from, well, 2 graph-like solutions starting from this cone. If the cone has, so there are 2 different expanding solutions starting from the same cone. What we have in this situation is the same situation, but at least 6 or any other number n, provided you take the initial cone close enough to the stationary cone. Okay, so the non-uniqueness becomes worse and worse and worse as you choose the initial cone close enough to the stationary cone. In particular, for the stationary cone itself, there exists If we look at the stationary cone itself, which expanders are asymptotic to the stationary cone? They are all these, so there are infinitely many. Right, so the stationary cone itself has a countable set of self-similar solutions that take it as initial value. Okay, so that's for shrinking solutions. So these are solutions, that was for expanding solutions. So those are solutions that start from a cone that has one singular point. And so we still have the same issue as in the three-dimensional case. Can we construct a smooth solution that forms a singularity, and at the time of singularity is that cone? So for that, we look for shrinking solutions. And here we get, so the picture is the same. I mean, it is literally the same. I just copied, there's a cut and paste. I replaced expander by shrinker. So here again, you can, so what happens here is to analyze the ordinary differential equation for shrinkers. The two pluses got turned into minuses. It turns out that for any height A here, there is a solution that exists for a short time, but now it doesn't exist for all positive values of C. It turns out that most solutions either turn vertical and then go around because they're geodesics in the XY plane, in the first quadrant for some metric. So this is completely normal behavior for a geodesic. In some circumstances, there's no singularity here, but as for something that has to be the graph of a function, this is a problem. Right, so a solution to the differential equation could end like that, or you could have for a different A, you could have something that does this. Okay, so now if you have a solution that does this, forms a vertical tangent somewhere, vertical up tangent, or somewhere forms a vertical down tangent, then there should be something in between that does neither. So there, in between these two choices of A, there has to be a solution that does not form a singularity and continues off. And such a thing you can then prove is asymptotic to a cone, and you can say something about the asymptotic slope of that cone. So because of that, you will what you would expect is that for most values of A, little a, the height here on the vertical axis, you would not find a solution, but for certain values of A, you might find a solution. So the theorem is there's a discrete sequence of A's going to 0. There's a discrete sequence of Aj converging to 0, such that the solution is defined starting from that value of Aj. The solution is defined for all positive x, and it is and those solutions are asymptotic to cones. So that means that this limit exists, and in particular, and then you can differentiate also. So right, the slope, you get convergence in C1 to the asymptote. So you get these solutions. So that means that we get a discrete set of asymptotic slopes. So it is not true that we get a shrinker for each cone. If I just draw an arbitrary cone here, most likely its asymptotic slope A will not be one of the AJs, little AJs that I have here, and there will be no shrinker that is asymptotic to this particular cone. Also, again, there's a theorem of Lu-Wang that says that if you have one of these numbers AJ, then there cannot be more than one shrinker asymptotic to that particular cone. If two shrinkers are asymptotic to the same cone, they must coincide. Okay, so and the other important thing is that these AJs, as J goes to infinity, have a limit. So we don't have an exact formula for them, but we can prove that they converge. So we get an infinite sequence of shrinkers, and in the limit, their cones converge to the minimal cone. There's no shrinker that is asymptotic to the minimal cone itself, but we can make shrinkers that are asymptotic to a cone that is arbitrarily close to to the minimal cone. Okay, so the conclusion is this. We have, so first of all, there's a sequence of shrinking solitons, asymptotic to a cone with aperture AJ. These AJs, or the cone, yeah, the slope, those slopes converge to the slope of the stationary cone. And then for each J, there are, we can find a certain number of expanding solitons, so expanders, that have the same asymptotic slope as the shrinker that we just found. And since the, right, and so in principle, Kj could be 1 all the time. However, the fact that the slopes of the shrinkers converge to the slope of the stationary solution means that the as J becomes larger, the asymptotic this asymptotic slope gets very close to the slope of the stationary cone, and therefore there exist many expanding solitons. So this number Kj goes to infinity. Okay, so now you can for each J, you can look at this. This is a solution to mean curvature flow. For negative time, you let it be just the single shrinking soliton that we found, and then for positive time, you let it expand it forward by choosing any of the finite number of expanders that we found with the same asymptotic slope. And these are weak solutions to mean curvature flow for various interpretations of the word weak. Okay, so this is an example of a smooth solution forming a singularity and then continuing, having more than one continuation, forward continuation. Right, so it shows that weak solutions are not necessarily unique. This is something Tom and I did in the 1990s, and we will have a reprint soon. There is a similar construction for Ricci flow. So, and there, so in particular, so with Dan Knopf, we worked out the same kind of situation for Ricci flow, and the results are very similar. The techniques are a bit more complicated. So here's the statement. We look for solutions of Ricci flow. So, okay, let me just explain the statement. So what we found is there is the analog of the stationary cone is a Ricci flat metric on R cross SP cross SQ, R plus. So there's a Ricci flat metric on this space that is conical in yet another interpretation toward cone. And so the metric is given by this expression. So this is a very well-known Ricci flat metric. So this thing plays the role of the stationary cone for mean curvature flow. And then remember, we had this Alencar solution that intersects the thing many times. So there is a Ricci flat metric on the same space that extends and that compactifies this part and turns it into RP plus 1 or DP plus 1. Well, you can extend to all of RP plus 1. Right, that interprets the R plus cross SP as polar coordinates on RP plus 1. So there was so that one was discovered by Bohm, and so that thing is the solution to ordinary differential equations. So there's no nice formula for it, but it exists. So there exists that thing also exists. It plays the role. So if that thing plays the role of the Alencar surfaces, then there's an analysis. Asymptotic analysis for metrics close to this that you get by piecing together a rescaled version of the Bohm metric with something around the linearization of the Ricci flat metric, and it leads to the following conclusion. So there exists, we have a sequence I didn't write it like that. But so, you know, for any k, you can find a shrinking soliton, right? So there's a sequence for each k. We have a shrinking soliton on dp equals 1 cross sq. And then there are k different expanding solitons, all of which are asymptotic to the same cone metric on, so all of which are, so the shrinkers and the expanders, they're all asymptotic to the exact same cone metric on R plus cross SP cross SQ. And so those metrics are of this form where you replace these coefficients by slightly different numbers. The same slightly different numbers for each fixed k. Okay, so and then if you put those together, the shrinking solitons form a singularity, or smooth solution to Ricci flow, form a singularity at time 0, and then after that you can continue them by choosing each any of these k different forward expanding Ricci flows. The analysis is so it's ODE analysis. You assume that the metrics that we look for have this form, that they are of the form ds squared plus ps, one function, unknown function ps for the radius of the first term and one cs for the second term. And then there has, because it's Ricci flow, you have to have this Lie derivative term. So there's a vector field that is also unknown. So you get, how many equations do you get? Phi and C both have to satisfy second order differential equations. So you get two first order equations for Phi, Ps, C, and Cs. And then F itself also satisfies the first order equation. So you get a system of 5 equations. And then by analyzing that, you can get the same result. Okay, so that's the Ricci detour. Then let me check the time for a second. I should finish soon, right? Yeah.
Well, okay. A couple of minutes, so.
Sorry. Yeah, a couple of minutes. So okay. What I wanted to end with is the following: that you can do more. Namely, what we did is we looked for self-similar solutions, which is sort of like it's the analog of differential equations of separating variables. You substitute something of the form square root of t times a fixed surface. So you can do variation of constants where you let the fixed surface itself evolve in time, right? So now our fixed surface n becomes an evolving surface, and we let it evolve by log of time. So it satisfies this equation: velocity equals mean curvature plus that lower order term. For the expanders, you can do the same thing by putting, removing the minus signs and allowing t, requiring t to be positive, and you get this. Then both are gradient flows, where for the shrinkers, this the Lyapunov function is well known. It's the Huisken functional. For expanders, it's a more problematic thing. So I write down this integral, which diverges. And so I don't want to say more about that. Okay, the PDE that you get is of this type. So it's the same ODE that we had before, but you get the DUDT in front of it. So this would be the expander flow. And what I want to say is that it's a quasi-linear parabolic equation of this type. So Vladyzinskaya, Udaltseva has all kinds of theorems about this for local existence. If you ignore those and you work in a different space, so you take a given expanding soliton, and you look at functions that are of the form that expanding soliton plus some small e to the minus gamma x squared f, where this f has to has to be a nice C2 alpha function. Then this equation generates, there's short time existence, but so, and here I'm not after the short time existence. What I'm after is the differentiable dependence on the initial condition, and differentiable in the sense of Fréchet differentiable in a Banach space, this being the Banach space. Okay, so you can prove that you have a local semi-flow in that space where the expanders that we found before are fixed points, and once you have smooth dependence on the initial data, the standard stable and unstable manifold theorems apply from dynamical systems. So what you could do is you could take one of the expanding solitons and linearize about it and see how many positive eigenvalues there are. And that, so this is what I want to end with. If you have an expanding soliton, let's say I have an expanding soliton, say I have this one. This thing generates a solution to mean curvature flow. If you linearize about it, you get this second order differential operator. And if this thing has positive eigenvalues, and they all do, then let's say if it has n positive eigenvalues, then there exists an n-dimensional unstable manifold of the space X alpha. So there exist solutions, there exist an n-parameter family of solutions that I've been calling W, this is what there is. This W depends on n parameters, m, because we have an n-dimensional unstable manifold. And for each choice of parameters, it's a solution to expanding mean curvature flow. So that tells you that in this space, in this space X alpha, you have U is a fixed point, and we have an n-dimensional family of solutions, none of which are self-similar solutions. So these are not solitons. These are even after going to the parabolic rescaling that we've been doing all the time, that I've been calling the expanding self-similar variables, these solutions are not stationary. So what this shows is that the set of solutions coming out of a cone is not just, we do not just have non-uniqueness in the sense that there are 2 or 3 or 5 or maybe n with n large enough solutions. What we have is a whole continuum of solutions. So the set of solutions is at least n-dimensional, where m is the dimension of the unstable manifold. So it's uncountably many, but even with a dimension. Then the Morse indices should look like this. So what one can prove from the ODE analysis is that the Morse index, as you go, if you go down here, the Morse index goes to infinity. This is a hand-drawn picture for Handingscape. What it probably looks like is that you have one that has index 0, and then there's another, then it turns around, there's another branch of self-similar solutions that has index 1, and there's another that has index 2, and then 3, and then 4, and so on. So this would be difficult to verify, I think, but the fact that the Morse index goes to infinity, that it's arbitrarily large, and therefore that there are solutions, initial cones that have, where the set of solutions coming out of the cone has arbitrarily large dimension, that one can do with an asymptotic analysis near the cone. Okay, and then finally, what comes out of the stationary cone is infinite dimensional, because you get the unstable manifold just has infinite dimensions, so you can produce families of arbitrarily high dimension coming out of the stationary cone. Okay, so I'll stop there. Thank you for your attention.
Thank you very much for this very interesting talk. Are there any questions? Maybe we stop the recording.